Welcome to part 2 of this slideshow about metamorphic rock. First, some unfinished business from part 1. Hydrothermal metamorphism occurs when hot mineral-bearing fluids enter a rock. Under the oceans, water penetrates fractured rock, mainly lavas, and when heated and circulated, creates hydrous minerals, serpentine and talc, from igneous minerals like peridotite and olivine. In continental crust, hydrothermal activity is centered around hot springs, near volcanoes, and above igneous intrusions into water-bearing strata. Dynamic metamorphism takes place in rocks buried to 5 or more kilometers, when the stress applied there is great enough to cause faulting. This cataclastic metamorphism produces a narrow zone of microbreccia with flow structure. The rock called myelinite. Stress at lesser depths forms other kinds of fractured rock. One is called cataclasite. A myelinite has some schistosity, but a cataclasite does not. Regional metamorphism occurs in 3 discrete venues. One develops at the roots of folded mountains intruded by felsic plutons. Another forms in rocks subducted at plate boundaries. And a third originates near spreading centers in oceanic crust. The geographic, thermal, and tectonic individuality of 5 large tracts of regional metamorphism, each with a distinctive pressure-temperature regime, led to their identification as suites. On this slide, the 5 black arrow-headed curves compare their temperature, pressure, and depth relationships. Located on the Pacific coast of North America, the central melange of the Franciscan suite includes in altered igneous rocks minerals that form only under extremely high pressure and moderate to high temperature. The Sambagawa suite on the Pacific coast of Japan was also developed under high pressure. But when the graph was drawn, none of the high-temperature minerals since found had been reported, so temperature is indicated as moderate, while in the continental crust of the Barrovian and Buchan suites of northern Scotland, pressures are lower, but temperatures attain very high levels. On this bare-bones chart, the Abakam suite of Japan, originally pellites, is indicated as a succession of facies related to high temperatures but low pressures over a tract much more extensive than those of the aureoles formed by contact metamorphism. Representatives of many of these suites are found in a number of localities worldwide. The 9 named stages or facies of metamorphism that together make up the suites are listed in this table. And on this chart, the colored blobs represent their temperature and pressure relationships. This second chart has similar limits to the facies, but includes orange separators that indicate the range of overlap between them. The sets of minerals that identify the successive metamorphic facies of mafic igneous and sedimentary rocks are shown on these 2 charts. The sets differ because of divergence in the kinds of minerals originally present in either of the 2 kinds of rock undergoing alteration. And this chart compares the minerals identifying the stage of metamorphism in a mafic igneous rock with that of a shale subjected to comparable pressures and temperatures. Here, slate and phyllite are taken to be at the low end of the green shift facies. Phyllite differs from slate in that slightly higher pressure causes crystals of cerussite, graphite, and chlorite to enlarge, giving the surface a sheen. This colorful chart lists the minerals in sedimentary rocks that characterize 6 stages of metamorphism, while this one offers the same information but is easier to read and more to the point, gives the names of the rocks that together represent the gamut of the zone. This chart lists in the order they are touched on hereafter the facies, that is, the named stages of regional metamorphism. All are silicates, for about 90% of the Earth's crust is composed of the hundreds of named minerals that are structural combinations of aluminum, calcium, iron, magnesium, potassium, and sodium, with silicon dioxide. Zeolites form when temperatures and pressures rise only a little above those of diagenesis. Seen mainly in pellites, they are porous cations of sodium, potassium, calcium, or magnesium, all with water attached. The water is driven off by heat, but can be resorbed, thus making zeolites uniquely useful. Prehnite and pompelliite form at somewhat higher temperatures and pressures. They are common in hydrated alterations of the oceanic crust around spreading centers. Often prehnite and pompelliite fibers or crystals fill cavities or are encrustations. Green schists owe their name to the presence of the commonly dark green minerals chlorite and actinolite in the Barrovian succession of stages. Amphibolite is characterized by the presence of hornblende. 2 examples show a typical salt and pepper appearance. The salt is probably potassium feldspar. Granulites form over a wide range of pressures, but their raison d'etre is very high temperatures. These are well above the melting point of many felsic minerals, leaving potassium feldspar, orthopyroxene, and garnet unscathed. Crystals are small, with poorly defined faces in close proximity, giving rise to a texture called granulitic. The blue schist component of the Franciscan suite is formed in subduction zones at depths of 15 to 30 kilometers. This produces glaucophane, the blue-green color, in basalts, but in the pellites of the continental crust, kyanite, albite, quartz, and garnet are characteristic. The culminating eclogite facies develops only in mafic igneous rock, usually basalts or gabbro, and is characterized by omphacite and coarse-grained garnet. The very high pressure suggests subduction to at least 35 kilometers, well below the floor of most continental crust. Along the bottom of both charts are the facies produced by igneous intrusions into sediments of the continental crust. Collectively, they are called hornfels. Each subfacies of these rapidly cooled fine-grained rocks is characterized by a suite of minerals named in succession albite epidote, hornblende, and pyroxene. Even higher temperatures produce the rare sanidinite facies. For those mutated rocks in which the original pigeonhole is still recognizable, the prefix meta is often added. Here is a meta-arcos, followed by a strongly altered meta-conglomerate, and 2 views of a meta-breccia. Altered igneous rocks, too, can be referred to by their origin. Pictured is a metabasalt and a weakly and strongly altered tuff, and a schist in which the original molanitic phase of alteration is still recognizable. Coming up, Geology for Everybody, Chapter 3, Stratigraphy.